to go out? And yes, it was. What gas was being produced? CO2. Okay, so I'm saying add the flaming splint test details to the front of your foldable. That way you can kind of have all your gas stuff in the same place. So here's the 3 situations, and we did go over 2 of these, and then I tried to go over another one, but it didn't work out. So let me start down here. This is an example of Alka-Seltzer. And Alka-Seltzer is just a little tablet. You stick in water and it bubbles. Well, guess what the bubbles are made out of? CO2. And so this guy's holding up this flaming splint, or gal, whoever, holding up this flaming splint, and then they stick it inside the mouth of the flask, and the bubbles will kind of attack it, and then what happens? Say again? It extinguishes. Yeah, I'm going to try to use our appropriate vocabulary. So CO2 will extinguish, right, a flame. So that's really easy to see, and you know, you can easily correlate that to what's in the fire extinguisher. CO2. So that's really easy. You're adding this to the front of your foldable so that you can have everything in one place, okay? All right, so the other gas, let's go up here. Okay, if you have a gas being involved and then you have a flaming splint, this is like they kind of blew it out, but it's still kind of smoldering, and then they put it in front of this gas that's in here. It causes it to ignite. What gas would that be? Oxygen. So you should recognize that oxygen will basically reignite a flame because oxygen fuels a fire. And so that's why we don't want to smother a fire with CO2 or some other form of kind of foam, and that will cause the fire to go out. All right, so the last one that's kind of not as common, it's not as familiar to you just in general in everyday life, is one like this. So these are actually 2 of the same situations. It's just 2 different styles of testing for the gas. So we have, this is a piece of metal, let's call it magnesium, and I have acid in here, HCl acid. So what's HCl's name? Hydrochloric acid. Good. What kind of reaction is that going to be going to form? Say again? I'm sorry, I wasn't sure if I was hearing synthesis or single replacement. Can you say louder? Single replacement. It is single replacement. And so this magnesium, and I'm going to tell you this will happen, okay? It certainly does occur. There's an evidence of chemical reaction because of there's gas being produced here. You just can't really see it because you can't see gas. All right, so magnesium and HCl. Who replaces who? Replaces the hydrogen, so it boots hydrogen out, okay, forming, I heard diatomic what? What gas? Hydrogen gas, diatomic hydrogen gas and magnesium chloride. How do you write magnesium chloride's formula? MgCl2. You haven't lost it, you're good. Okay, so balance that out. Right, you see 2 hydrogens and 2 chlorines, so I see 2, there's a need of a 2 over here for hydrochloric acid. All right, so first of all, we made a gas. What's the gas? Hydrogen gas, and you can't see a gas, so you always have to test for a gas. And so if I put a flaming splint in there and it catches on fire, well, that's probably oxygen. If I put a flaming splint in there and it goes out, extinguishes, it's going to be carbon dioxide. Or you get the special scenario where you put your flaming splint in there, it goes like that. Okay, so it's called the hydrogen bark test. Doesn't that kind of sound like a dog? Like you stepped on it? It was like, oh! Yeah? Okay, so that's called the bark test, or the hydrogen bark test, or the hydrogen pop test. It's just pop doesn't sound like that, so I always go with bark, because it sounds like a bark instead. So it actually makes a sound. And so another way to do it is, instead of just putting it in a flask like that, is you allow for your reaction to happen down here. You collect your bubbles in a inverted test tube, so you capture your gas just like you did yesterday, but you did it from underwater, and then you hold the flaming splint up here to the mouth of the test tube and it goes Arr! So it's called the hydrogen bark test. So those are your 3 tests for gases. Okay, you got to know those. Give me thumbs up. You good? Alrighty. All right, so let's go ahead and do Kahoot next. Yeah, let's do that. Okay, does everybody get logged on? Everybody get there? Okie dokie. So this is going to help me figure out what your misconceptions are with what's that KMT stand for? KMT? Kinetic molecular theory, which is the theory that describes kind of how gases behave with each other. And it talks about the ideal gas law quite a bit, so I just want to make sure that you're familiar with this enough Here we go. You got your code? 7677817. Figured computers are easier, especially since we have no Wi-Fi. No Wi-Fi. All right, I got all kinds of people joining. All right, so this one's pretty short. It shouldn't take us more than about 10 minutes, really. But we're almost done with gases, so you'll soon be expecting a quiz on gases. And if you feel really comfortable with problem set 14, you should be pretty good. Today's information is kind of related back to stoichiometry a little bit, which is why I wanted to give you a chance to start looking at that sooner than later. And I think we'll be able to master that today. I think we got one more person. Oh, no. Sydney's not here. Okay, let's roll. Okay, so where's my sound at? Water droplets that appear on a steamed up window are produced by what? Sorry, I'm trying to get out of the way. I can't see you. I just stand up in the back. All right, so condensation. So we're taking water to water vapor. Good. Next. Oh, hold on. What law is represented by the picture below? Thank you. And, oh, okay. Ooh, that's a bad spread. But we did have a lot of people see that. What were the variables that were shown in the picture? Pressure and volume. And you know pressure and volume is going to be who? Boyle's law. If it were temperature and volume, it'd be who? Charles' law. So you've associated the scientist names with their appropriate formula. Nice. Which of these can be easily compressed? Think about what compressed means. All right, so easily compressed was the term, right? So you want to have a lot of space between your molecules so you can squish them together quite easily. Liquids cannot be compressed really easily. You have to really knock them together if you're going to try to compress it. Good. All right, what would happen to the pressure of a tank in a steel tank if it was heated? The pressure of a steel tank was heated. All right, doing well, guys. So, can someone explain that to me? Go for it, Tyrion.
As you heat it up, the molecules within the tank would start to move faster and start hitting the side, which is what pressure is.
So what's the definition of pressure?
When the molecules are hitting off the
What's another word we could use for hitting off the thing? Collisions with a container wall, right? So pressure is just simply number of collisions with a container wall. If you have like 5 collisions, it's pretty low pressure. If you get like 5 million collisions with a container wall, really high pressure. What are you saying is causing more collisions?
the heat is that way the molecules go faster and hitting it.
Because temperature is correlated to average kinetic energy, so meaning energy of motion, right? So if you increase the temperature, you increase the kinetic energy, they move faster, they bombard the container more, meaning pressure would increase. Good job, guys. Got to connect kind of all those dots, make sure you're good. Which of these takes the shape of the container it is in? All right, so I can see maybe well, no. So if I have a container like this, it's closed, well, a liquid would easily fill that, right? If it were filled, it would take the container's entire shape, and so would a gas. Solid certainly would. Like ice isn't going to morph into like this cup shape. So I can maybe see why a couple of you guys chose liquids only, but gases will as well. All right, temperature and pressure are blank related. All right, so that's in your foldable, right? So I'm feeling pretty good about that. I got 20 of you guys there. Remember, increased temperature increases pressure. That's what Tyrion was just telling us about. Gas will always occupy the total volume of the container. You can't say I don't care. It's not the correct answer. Yay! No! will. Gases have no choice. They will expand until they meet the edges of their container, meaning they will fill up their container entirely. Think of a balloon. Are you going to blow in a balloon and it's going to be like, no, like, I only want to feel like half this side. No, it's going to take up the entire space available and keep pushing outwards. All right, what would happen to the volume of a gas in a balloon if it was heated? All right, we're doing great. So why? Okay, because they're directly related. I hear that, but tell me, you have your box of air. There's a box of air. Whip it out. Okay, increase the heat on your particles. What are they doing? They're bouncing around crazy, right? What's happening to the pressure? It's going up. Does it say pressure can change? So you're assuming it's constant, right? Well, how do I keep a constant pressure with stuff moving fast inside and bombarding the container? Make a bigger space so they don't collide with the container quite as frequently, aka bigger space, bigger volume. So there's a lot of little box of air things you can kind of do in your mind, and it's very commonsensical. It's nice. What is STP? Guys, try to keep it interesting. Okay, nice. I'm not going over that one. Moving on. Which state of water do the particles move about most freely? Nice. Overall, gases do move. They have the highest kinetic energy. They have the most motion to them. They are moving about very freely. Limited intermolecular forces hold them together. There's a lot that can go into that. What is there between the particles in a gas? Oh, right. Yes, no trick questions on you guys. You got it. So yeah, nothing. There's nothing between particles of gas. Next, Gay-Lussac's law describes the relationship between all right. Ooh, I think probably what's going on here. These 7 people. We just haven't memorized our relationships with the scientists' laws and such. Okay, so that's Gay-Lussac. So you look at your folder for that. If the pressure of a gas goes up by 5, the new volume will be okay, so tell me again. I think we already answered this one. No, we actually didn't. Pressure and volume. You have a pressure, right? Increase the pressure in your container. Take your container out, guys. Come on. Okay, so increase the pressure in your container. Okay, so what happened to the volume? It shrunk by, okay, so if I increase the pressure 5 times, what's happening to the volume? It goes down because it's inversely related, so it goes down by 5 times, which is 1/5 of its original volume. You got me? Easy mathematical relationship. Took 3 seconds to really think about, but you just didn't think about, like, how does it change intermittently. All right, next, you're on fire. Okay, based on Boyle's law, if the volume increased from 20 to 60 liters at 60 atmospheres, new pressure is you can do it. Okay, so, well, okay, I tried to read it really fast for you guys. Look right here. We're going from a volume from 20 to 60 liters. What happens to the pressure? Hold on. Here's your box of air. From 20 liters, now it's at 60 liters. So is it colliding with the container? Not really. So the pressure goes down. Which of these is down? Red or yellow? Okay, so you've narrowed it down. And then you're looking at the numbers. Well, 60 atmospheres, I did that really so that you could just do the math quite easily. So the inverse of that would be 20, or the opposite of that in this case would be 20. So that's your P1V1 equals P2V2 with numbers that are the same, so you can figure out the other one. You go with that now? It was probably just the timing, if anything. Okay. Next. What would happen to the pressure of a gas inside a syringe if you compress it? So syringe looks like this. Okay, you guys are easy peasy. Okay, so you're compressing something, of course, it's going to increase the pressure. Next, the ideal gas law constant is, or R constant is, look closely. Ooh, okay, so I'm thinking reading closely was the only issue. Any questions there? 0.0 HE1, I'm Sir from Mulkay. I have this girl who we played softball together. Her name was Mulkey. We just called her Mulkay. Never mind. You guys are lame. Okay. What are the conditions at STP? Once again. One more person. Okay. So that's on the front of your foldable. You've seen it a number of times. Make sure you keep looking back at that. Good job. PVs on RT is known as the combined gas law. Oh no! Okay, what happened? Because you were like, of course it would be yes, because everything is yes. No, I was hoping somebody would say duh. Yeah, thank you, whoever that was. You keep me happy. Yeah, so that's a no. What is the combined gas law? PV and T equals PV and T, right? P1V1 over T1 equals P2V2 over T2. Next, and almost last, when using the ideal gas law, volume must be in. Volume must be in. With me, Omar? All right, okay, liters, very good. I think you know that now because the ideal gas law constant has liters in it. You're good. To convert Kelvin into Celsius. Omar, are you with me? Okay, you guys, that didn't trick you, right? So instead of going from Celsius to Kelvin, I went from Kelvin to Celsius, so you subtract 273 versus adding from the other way around. All right, who feels pretty good about that? A couple of you guys, hold on. Get the results. Boom, 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 boom. Nice, guys. Let me download these results real fast and see where our misconceptions are. We are good. First person gets extra credit in my heart. You are so right. I try to award you for extra work, not just mastering what I've asked you to. All right, so let's finish up Graham's law real fast. Maybe as soon as my computer moves. Oh, I gotta have you guys do this. This is for an assignment for this this thing I'm in. Glee cohort. Yeah, I'm in a Glee group. It's called Gifted Learner Education. Gifted Learner Education Endorsement. Okay, so quick, can you guys do a quick reflection on these index cards for me? It's right here on the board. Pretty easy to do. Take a minute or two. And I'll put Graham's law on the board so you guys can copy this information now. So, first question on the board is, alright, so first thing is, what's the value of using technology as a way to differentiate instruction? So do you feel like including technology somehow benefits you? Think about for yourself, take a sentence or two, whatever you need to write there. So for example, instead we used videos instead of just drawing something. So like you're making a product, or we used compute instead of a quiz, like a traditional handwritten quiz. So, or using the CK12 website versus and repeating herself a million times of straight geometry, whatever it is that you guys want to think about as technology, you guys are very aware with that. I don't think I need to explain that too much. So it's kind of just an idea to think about. And then the second question, and it says minimum 5 sentences, right, however long you want to. More than one sentence would be preferred. But how does using technology or does it increase your knowledge or learning, and does it kind of keep things interesting? Right now, we kind of just reflection on uses of technology in education. You can even get information that might help for the rest of the year. Things that you really like, and things you're like, oh my gosh, I'm so over this. One person last year told me web quests were so last year. And I was like, well, chemistry, particulate diagrams, you can't really see everything up close, so we have to get creative. Take like 1 more minute where you are. Is it okay if I scooch forward? You don't have to. No. It's just information that I can use. Is it okay if I scooch forward here? Most of us are saying yes. Alright, so you're going to add this gram slot section to your folder as soon as you're done with your little reflection, and I'll take those as well. When you collect the index cards, everybody's going to collect the index cards, so just hold them up, or maybe one person at the table can collect them. Thank you, sir. If one person at your table can collect the index cards, it helps a lot. Any other index cards? It's okay, I'll get some experience. Thanks, guys. Appreciate it. Appreciate it. I graduate from Glee on Thursday. I know you're interested. gotta finish my homework though. Okay, so Graham's law is pretty simple. As a quick demonstration, I know you're still writing down some of this information. I need 3 fantastic volunteers. Mikado, Isabella, and Avery. Come on. Volunteers, voluntold. It's really similar. So, okay, so I got Mikado, who's going to be oxygen. You guys see oxygen over here? I got some nitrogen, and I got some helium. Okay, so you're going to turn your oxygen up, right? Sorry, my bad. All right, yeah, that one. There you go. Okay, so using this thought, the rate of diffusion, which just means speed of travel, of any gas is inversely related to the square root of its molar mass, right? So it's just basically inversely related to its molar mass. So here's what that really means. Heavy things move slow. Light things move fast, right? So heavy things are not going to move fast. So that's like the inverse relationship to that. So we're going to have a quick race. Okay, so you have to stand. Okay, here. We'll stand here and just move towards the room. So they have to move at their respective speeds based on the molar mass of their gases. So they're going to demonstrate that for us right now. Okay, why? How much does helium weigh? Everybody here can tell me.
0.0.
Say again?
1.0.
That's
4 grams.
about 4 grams per mole, right? What does Avery nitrogen weigh? No, that's just N.
28.
28. It's diatomic gas, right? It's nitrogen, so always 28. And then Mikado weighs 32. Okay, so can you do a reverse speed? You gotta move faster. Okay, so basically this is like all gases that are in our, think of our scuba diving tank or think of a balloon. If you were in a balloon, okay, so pretend there's a big balloon around them, and there's a little hole in the balloon. Who is going to move out of the balloon the fastest? All right, come on, helium, go back to your seat. You're out of the balloon the fastest. Okay, so it was kind of floating, the balloon was floating, and then it's kind of fizzled out because the helium just escaped to the rest of the world. And then which gas is the next to kind of be predominantly gone? Diatomic nitrogen, because it's like, yeah, I mean, I'm moving at a medium pace, and it's going to stay afloat some. But then when you have leftover in the balloon, predominantly oxygen, because it's the heaviest of them all, so it's going to kind of stay in the balloon because it can't diffuse quite as fast. So that's really what Graham's law is. It's about how fast particles move based on their molar masses. Thank you, my volunteers. Appreciate you. Okay, so based on that kind of description, what is a fusion? What's it really similar to maybe? Diffusion. Think of biology, right? How is it described in biology? Right, so I'm hearing high to low, and that was like movement of solutes and like glucose and other nutrients in the body, water, but that's osmosis, but similar deal. So fusion's really similar, but we're talking about gases. So diffusion is the escape of a gas through a tiny hole in the container. And of course, if you're inside of a container, you're really, really concentrated. And if it's outside the container, it's not so concentrated. So the flow of high concentration to low concentration still applies. So my container is going to be a little balloon. Okay, so we got our little balloon. We have our particles inside the balloon. And I'll mix that with some heavier particles that are red here in color. So I'm giving you some examples and some images that you might be adding to your photo, kind of kill 2 birds with 1 stone. And oh no, there's a little hole and it pops. And the balloon's going to start to let a gas in particular escape. Which gas do you think will escape first? Red or blue? Why blue? Because I've drawn it smaller, so you're thinking it's a smaller molar mass. So yeah, so it's going to start to escape from high concentration inside the balloon to low concentration outside the balloon. Eventually, yeah, most of it will escape. So think about though, back some awesome birthday, you got a balloon. Okay, so you're thinking about your balloon. What happened to the balloon over time? Now, when it deflated, are you talking about like pancake thin? It's flat as heck and it's totally deflated, or it's kind of like. So there's still something in there. Why? Well, have you ever had a balloon go pancake flat? Unless you just like let all the air out yourself, you squished it and you sucked all the helium out, and you got like this. No, okay. You know what he did that? I know you guys did. Don't lie to me. Okay, so everybody does the helium trick. So what eventually will happen is the gas particles that we're showing here, they move to low concentration, but not every single one of them will escape because there's particles all out here, right? There's all kinds of particles. There's different particles out here. So they're all bouncing around the outside of the balloon, the inside of the balloon. So what can happen is they can also bounce and collide with the balloon's like little empty hole here, and it can kind of keep some of the air inside the balloon as well. That's why it doesn't go pancake flat the minute a hole gets poked into it. Sometimes it does if the hole's really big, but like a small tiny hole, it won't go 100% flat. So there's an equation that relates this, and it's 100% this little description up here. And it is, so you see the description, the rate, so I'm going to take this rate of effusion is equal to, or is inversely, so what does inversely mean? So indirectly, so is whatever I'm relating, is it on the numerator or the denominator? If I'm saying rate, and this is, I can just put this over 1 if that helps. Rate is inversely related to the square root of the molar mass. So what I'll put square root of molar mass on the numerator over here or the denominator over here? The denominator, because that's what inversely related means. So it's actually, the rate is equal to the inverse of the square root of the molar mass of the gas. So the rate that gas moves is related to this inverse of the square root of the molar mass of the gas. So I basically took that and put it into a formula. So what's probably going to be here on top? If you had to put something here. Probably 1 just be a placeholder. So this is actually the formula called Graham's law, but many times we don't think about a singular gas going, how fast does a singular gas move? Many times we're actually comparing 2 gases. So like I compared 3 gases over there, that I couldn't put a formula, but I can compare 2. So the comparison of 2 means I put 2 of these right on top of each other, and I can compare 2 rates to 2 molar masses. So as you compare 2 gases, it looks like this. Rate 1 over rate 2 equals the square root over the square root. Okay, so I'm basically taking this and I'm just flip-flopping it again. So rate 1 is this gas. I'll put the molar mass of rate 1 down here, or the molar mass of gas 1 down here. And then rate 2 is this gas, so I'll put the molar mass of gas 2 up top. So I can show the inverse relationship here. So this is the one we will likely use most of the time. So if you're writing down your formulas and you're comfortable, I would write both, but just kind of put a star over here on this one. Oh, and trick for you for later. We always use the lighter molar mass as 1, or rate 1 or molar mass 1 here, because it makes sense to do that, because in the end, if I'm like, yeah, helium travels at 0.25 times as fast as something else, 0.25 times as fast just doesn't make as much sense to many people. Instead, I could say oxygen travels, 5 times faster than carbon dioxide. So that makes more sense. So we always try to use the lighter mass, or molar mass, as the rate 1 and molar mass 1, because it makes our mathematics make more sense. Okay, so let's actually do a problem with this. Oh, I'll show you why this matters in a second. Okay, so here's the question that could be relating to gases. You can see my 2 gases are what? Hydrogen and carbon dioxide. Okay, so you're already thinking, okay, I've got both of those. I'm going to have to use the rate over rate equation, which is rate, what's my equation again? 1 over rate 2 is equal to square root molar mass 2 over square root of molar mass 1. Okay, so who's going to be the 1 here? Why hydrogen? What does hydrogen weigh? I hear it. Okay, so this is hydrogen gas. Now it's understood that's diatomic because it's a singleton kind of by itself. So this is H2, which weighs 2 grams per mole, something like that, right? What does this weigh? Anybody? You can add about 44 grams per mole. So I'm taking C, carbon dioxide, O2, that's 44 grams per mole. All right, so we've already identified the gases, we've identified their molar masses. Now I've just got to plug them in and find the comparative rate. So it says, what is the rate of effusion? That means I'm looking for this like differential rate here, and I'll help you finish this up here. All right, so rate 1 is going to be about hydrogen, and rate 2 is going to be about carbon dioxide. So I like to label them so everyone's very clear on what we're talking about. And that's equal to the square root of, what's the molar mass 2? That say again? That's our 44 gram per mole molar mass, because that's about carbon dioxide, right? So you're putting it opposite. And then this one, 2 grams per mole, and that's the hydrogen gas, which is opposite here. So calculators out. Let's do the math. How are you already put it in your calculator? Michaela's got all the calculators right. What are you guys putting in your calculator? So if you're putting square root of 44 over 2, you got to double up on parentheses or make sure everything's contained. Or you can just put the square root of what? 22. Okay, so 44 over 2 is 22. So what's the square root of 22? 4.69. Okay, notice that I didn't write any units. Why? Because grams per mole cancel here and here, right? Okay, so this is just a rate. What the heck does that even mean? 4.69 what? That's the relative velocity of who compared to who? Yes, hydrogen compared to carbon dioxide. So to put this into words, which I would expect you to do and be able to understand, is that you're actually saying hydrogen moves, or fuses, I'll use my correct vocabulary, sorry, diffuses at 4.69 times faster than carbon dioxide. And so didn't you already know hydrogen would move faster? Why did you already know that? It's the lighter one, right? It weighs 2 grams. You already knew it's going to move faster, but now you're actually saying how many times faster it's moving. It's almost moving 5 times as fast as carbon dioxide because it's 44 grams per mole, so it's moving quite slowly. So does that make sense? And why we're doing the comparison now? We're actually comparing them, how fast they're moving within each other. Give me a thumbs up if I can move on to the next example and last example for now, okay? All right, so this one I want you guys to take a second to read, and you set up how you think you should approach this. You write this in your notes or on the folder of your place, but we're going to do some straight geometry after this, so we got to get this last one done. Anybody want to tell me the general setup here? We can take a stab at it. Ashton, tell me what you think I should set up first. Okay, so what is the molar mass of krypton gas? So we're first identifying what's krypton's molar mass, because we know we're going to need it eventually. 83 point what? Okay, so we know that. And it says an unknown element, elemental gas, so an element from the periodic table that would be gaseous. So that's our unknown. It uses 4.5 times the rate. So that means it's faster. Are you reading this and seeing that this is faster? What does that already tell you? It's lighter. Okay, so we know this is the lighter one because you're reading between the lines and seeing it's faster, so it's lighter. So we're going to call that one rate what? Rate 1. Or molar mass 1, whatever you want to correlate that to. This would be rate 2 or molar mass 2. All right, so we are reading between the lines. You see that. So now tell me, guys, what you want to set up next. Say again? Okay, so I'm writing the formula. I'm going to write rate 1 over rate 2. Well, I already know what these are, right? Okay, so I'm just going to label them unknown, because that's my rate 1. And this one's my rate 2, so that's krypton. Oh, that didn't work out. Okay, so that's krypton. All right, what does this equal? They already told us. Yeah, we already know their comparative rate is what, William? It's 4.5, because that's what they said. It's 4.5 times faster. Okay, so that's just kind of telling me the value of this. But now, what do I write? Where's my molar mass stuff come in? So 4.5, which is the relative rates of comparison, is equal to the square root of, why are we putting 83.8 on the top? Because that's krypton, right? And they're inversely related. So we're going to put krypton's mass up here. I'll just put that here just in case. 83.8 grams per mole. And then who goes on the bottom? The unknown. And do we know the molar mass of the unknown? No, so I'm just going to put what here? X. We're just going to solve for X. All right, so basically you guys said, I know the molar mass relationship is 4.5. The square root of 83.8 over X is equal to 4.5. So how do I simplify this math? Square what? Square everything. Square both sides, right? So squaring all of that, what's 4.5 squared? Calculator, please. 20.25. Is that what you said? 20.25 is 4.5 squared. What's the square root of blah, blah, blah over X squared? Just 83.80 over X, because the square root squared cancels out that, because that's the inverse relationship. Okay, so now how do I get X out? Multiply by X on both sides and divide by what? So this cancels over here, right? So then divide by 20.25 on both sides, and that cancels over here. So X has been isolated, and what's 80.8 divided by 20.25? 4 point what? 4.138. I believe you. That sounds weird, but I believe you still. It just sounds a little off, but I'm fine with that. About 4. Okay, so X is about 4 grams per mole. Who's that? Yeah, I know, but who is it? What elemental gas weighs 4 grams per mole? Helium! Okay, so this is our helium gas. We just identified it based on its molar mass. So reading that question now, do you see where your pieces, they're all the same pieces. It's just we had one thing that we didn't know, which we previously did. And so you can identify elemental molar masses that way. All right, I want you to get up and take a stretch break real fast, because I have a couple more questions you can use stoichiometry, and I don't want you to be sleepy on me. So get up and go talk to somebody about what you're studying for your AP exams, or what you did over spring break, or some other unknown issue that you need to discuss. Stretch break real fast. I just want you to get done like Wednesday, Thursday. I don't know, because we're almost done with gas. I don't know what you're because I walked in that car. All right, back to your seats in 5, 4, 3, 2, 1. Take a deep breath. Here we go. Okay, so let me tell you the premise of this first. And you, of course, need probably to write down at least some of the ideas here. Every single idea, maybe not, but the general ideas are, we have 2 situations we usually deal with gases. If I say STP, you automatically think of what conversion? STP, what stoichiometric conversion? 22.4 what? Say again? Liters of gas per 1 mole of gas, right? So if I say STP conditions, standard temperature and pressure, your mind just automatically goes 22.4 liters per mole because you've seen that, gosh, since like February or so. Gosh, it's almost May. So this is something that's very common that you already know based on our old stoichiometry mole relationship stuff. Now, is everything at STP? No. So if everything's not at STP, you cannot use 22.4 because it's not at the conditions that a conversion is appropriate. So if I say, 100 degrees Celsius and 5,000 atmospheres or something, you're like, okay, Celsius, I can convert to Kelvin. And pressure, I can totally get to atmospheres if it's not in atmospheres. And many times, not only will pressure and temperature will be given, but volume will be given as well. So if you have those types of conditions given to you, you're like, oh, that's easy. I can use the ideal gas law. Because if you can use the ideal gas law, and I'm asking you for moles of something, well, that's just asking for N. Versus you using this to get to moles. Do you see how they both can get you to moles? It's just, this one's nice because it's just one number. Plug it in as at STP conditions. Whereas this one's like, okay, I got to use the ideal gas law, but I can still do that. I'm very comfortable with the ideal gas law now. So in either case, if I can get you to moles using STP conditions or non-STP conditions, and you're using the ideal gas law to get to moles, I could then say, okay, well, how many grams is that? How would you get from moles to grams? What's the conversion factor called? Moles and grams? Molar mass. So that's just called molar mass, right? Well, molar mass is just grams per mole or moles per gram, depending on which way you need to flip your units to work with it. Same thing here, though, right? If you get to moles, you could easily get to grams using molar mass. So they both, in the end, use molar mass if you were to get to grams using stoichiometry. So those are relationships we already know, right? So here's where we actually have to identify, hey, am I dealing with a gas or not? So remind me one more time, what is this PV equals nRT called? Say that middle word really loud.
Gas.
Gas. Okay. It's the ideal gas law. So should you be putting solids and liquids and other things like that inside of this? No. So I will give you a problem and say, oh, magnesium chlorate decomposes. Magnesium chlorate, that's a salt. How do I know it's a salt? What's magnesium chlorate before I move on? I hear magnesium chloride so far. Any magnesium chlorate? MgClO3, parentheses, where's this 2 coming from? From magnesium charge. And what's chlorate's charge? A 1, so I'm going to keep a 1 right there. Okay, so magnesium chlorate is a salt because it's actually ionic. How do I know it's ionic? What did I do to get the formula? I crisscross charges, and only ions have charges. So this is not a positive charge, this is a negative charge. This baby is ionic. Is an ionic compound ever a gas? No, it's a solid. Think table salt, right? It's a solid at room temperature. It's never, ever a gas. So I cannot put anything with magnesium chlorate in the ideal gas law because it's not a gas, right? So if I say magnesium chlorate decomposes, you're thinking, okay, decomposition. It usually makes a gas. What gas does chlorate decompose to? Say again? I hear oxygen. Why not chlorine gas? It's deadly. It would kill us all, right? We're not going to be making deadly gases. All right, so what does magnesium chlorate decompose to? I'll write this over here. Just to practice our reactions, you're seeing now I want to make sure we're feeling okay with everything all collectively together. So you said it makes what gas? Oxygen gas. Okay, so I'll put O2 there. What's still left over here that needs to be produced? Say again? Metal chloride. You guys have your metal chloride up here, and who is that? What's magnesium chloride? Cl2. Okay, and now I'll balance it with a 3. Is that right? And then 2. Oh, it's already balanced. Okay, never mind. So this 2 right here goes to chloride, Cl, and Cl over here. Okay, so here's what we have. I can start you off with grams here and say, okay, tell me the pressure the gas produced at the end. Well, I can't plug the grams or the moles into the ideal gas law because it's not a gas. So I would go from grams and convert to moles of magnesium chloride or chlorate. Still not a gas, right? Well, how do I get to this gas from here? What do you mean by that?
Use like 3 moles of oxygen to 1 mole of magnesium.
So mole ratio?
Yeah.
Okay. So I would use molar mass of this magnesium chloride to get from grams to moles. That's easy. We've done that a million times. Then to get from magnesium chloride or chlorate to oxygen, aka moles of that gas, I'm going to use the mole ratio from the balanced chemical equation. You with me? Now I'm in oxygen. Heck yeah, I'm in moles of oxygen. I have N. I can plug that into what? The ideal gas law, PV equals nRT. And I could solve for pressure or volume or temperature. I could solve for anything because now I have the N, which is the gaseous moles I was looking for. So now we're just going to basically take this and put this into perspective. Okay, an example speaks more than me walking through the steps right now, okay? All right, so you guys okay? I'm going to start with you guys now on an ideal gas law application. All right, so looking at this one, read and write down every given right now. Write down every given. I want to make sure you're with me, so halfway close to your computer so I know that you're with me 100%. I'm probably going to do about 2 or 3 examples, so make sure these are really healthy and you're writing down every detail so that you're very comfortable later. Frank, tell me one of the givens you're writing down. Okay, so that's pressure. So he says P is equal to 755 millimeters of mercury. All right, Makeda, tell me another given you're writing down. Okay, so your temperature is 23.0 degrees Celsius, and then you said Celsius. 296 Kelvin. Good. So that was kind of an automatic. It's almost like you put a period at the end of the sentence every time you wrote a sentence. Now you're doing that with Celsius to Kelvin. Who else? Who else wants to give me another given? Meredith. Is our volume, right? Okay. And then Zach, give me one more.
Well, I was going to say, doesn't like pressure and the volume have to be in like atmospheres?
Very good. So you're already seeing ahead. You're looking far ahead into the ideal gas law, and you know, because we practiced the ideal gas law quite a bit, they have specific units because they have to match with what? What constant? The R constant, right? So now that we already see that, I know I'm going to have to go to atmospheres, and I know I'm going to have to go to liters. I'll go there in just a hot second, okay? So we'll get there. What else is here that gives us information about something? Yeah, Sophie. Aha. So this decomposes, right? So you're thinking, okay, decomposes. I got to write a reaction, right? So what's potassium chlorate? Somebody shout it out. O3. So this is chlorate, ClO3. What's potassium's charge? 1. And then chlorate's charge? 1. Crisscross, we're good, right? Okay. We just did a very similar example. Think. Decomposition, what gas does this make? What oxygen does this make? This makes oxygen gas. Okay. I'll write that O2 over here, diatomic, and then what's remaining? So the metal chloride, and you know that's KCl, but you're not just saying it's because it says KCl there, you crisscross your charges again. K1 plus, Cl1 minus, crisscross. All right, you guys balance that, tell me what you get. 3 where? 2. Well, tell me, you said the 3 and the 2, right? 2 KClO3s and 3 oxygens. Okay, so that's 2 times 3, so how many oxygens are here? 6 and 6, check. And then what else? 2 in front of potassium chloride. Okay, so we're trying to get back into that chemistry and language we've been speaking for so long. So we have this great reaction. All right, so the question is how much, what's this asking for? Grams. Thank you, remember much means grams. How much of what? Say again? Potassium chlorate was decomposed. It has nothing to do with oxygen, but we're going to have to use oxygen to get what we want and then backtrack here. So let's talk about the whole process first. Actually, let's before we do that, Zach said let's go to atmospheres. Tell me how you get from 755 mils of mercury to atmospheres. So you're doing 755 millimeters of mercury times what over what? 1 atmosphere over 760 millimeters of mercury, making sure you're not just memorizing, you're actually using your stoichiometry. What is that in atmospheres? Point what? 993 atmospheres, okay? What is this in liters? What did you do? Move the decimal back 3 places. 1, 2, 3. Okay, so that's 0.426 liters. Okay, everything is in appropriate units, right? You can see that you're using the ideal gas law here. So before I move on, you see PTB. What do you not see? Say again? You got R up here, right? I'm not going to write R out. We know it's there. What else are you missing? N. Okay, so here's the real question, guys. I'm solving for N, and then I'm going to backtrack and solve for the question you actually asked, which is grams. This is going to be regarding what chemical, though? N. What is this law called again? Ideal what? Gas. You're solving for what? Oxygen. That is the hardest part to see. N of what? It's the gas of interest. Who cares about gas and fire? I can't touch a solid with a gas law. It is a gas law for that reason, because gases make pressure and they have volume. Solids, not so much, right? So when I solve for P, or I use PV equals an RT, and I'm looking for N, isolate N for me first. I'm here and divide by RT on both sides, and that cancels over here. So rearrange, and we now have N. I'm just going to rewrite this for my own purposes. N of oxygen, this is just a little reminder to myself, I'm solving for oxygen, is equal to PV over RT. You with me? Okay, the hardest part is recognizing what you're solving for, which is N in this case. All right, now this is cake, right? What am I plugging in? The numbers. I'm ready when you are. What's my pressure? 0.993 atmospheres. Okay, what's my V? Liters. Okay, over, what's my R? Atmospheres, liters, over. Okay, and then 96 Kelvin. All right, before we move and calculate, tell me what cancels. Ansley, tell me one thing it cancels. Atmospheres on top and bottom. I think that's blue. Will, tell me another. Kelvin on top and on the bottom, right here. Shelby, tell me another. Liters. What's left, guys? Moles, right? It better be. That's what you're solving for. So kind of double check, make sure you're good. Calculate your moles, how much you get in like 10 seconds. I gotta catch up with you guys. Help a buddy out if they need it right now. Yeah, I'm guessing small number. All right, so N of oxygen is equal to 0.001741. I'm not rounding because is this my final answer? No, the final answer is asking for grams of potassium chlorate. We're just not there yet. All right, so this is moles of O2. Give me a thumbs up if you have made it here. So none of this is new, right? Because we've done reactions forever. We got ideal gas law pretty good. We've been doing our whole givens and kind of interpreting what to solve for. Now this is just combining two old things and it's going to look new. It's not really all that new. So I have moles of oxygen. What was my question once again? Grams of potassium chlorate. Those aren't the same thing, right? So how did I get from A to B? Balanced chemical equation, mole ratio, right? So I have that right here. Can you guys see? I don't want to, maybe I can make this a little bit weirder. It's still not great. You guys have your reaction right in front of you, right? So if I move that up like that, it's not too bad. Okay. Okay, well, I tried to get on the same screen. So I have this moles of oxygen, right? I'm just going to go straight from here. I'm going to convert to the thing of interest, potassium chlorate, using what ratio? What's my number that goes with oxygen? 3 oxygens. Where am I going to put that? Bottom, because I want moles of oxygen to cancel, right? And that's going to go for every what? Of potassium chlorate, right? So 2 moles of potassium chlorate, 2 moles of potassium chlorate, KClO3. Okay, still not to the end. What's my last step? Okay, I'm going to squeeze that over here. What am I putting? Notice that the moles of oxygen do cancel here. Now I got to get moles of potassium chlorate to cancel. Where do I put that? On the bottom. What do I put down here, though? How many moles? 1, because anytime you're doing molar mass, you only compare 1 mole of that compound. And what's the 122.55? Thank you. 122.55 grams of potassium chlorate if you added up your molar masses. And drum roll, let's know what your answer is when you get there. That says 122.55 on the end. Sorry. Frank, what'd you get? Can I get a second on that? A lot of you guys who are not calculating, I hope that you don't make any stupid mistakes in your calculator just from lack of practice. And that's grams. Okay, cool. All right, so backtrack here. What did we, oh, hold on, how many stick pigs should I have? That's right, 3. Yeah, 3 stick pigs all the way, we're good here.
Do you use 3 if you have Celsius?
Yeah, it's right here. So yeah, well, that's 23.0, so 3 stick pigs.
Okay.
And so is that one, and so is that one, so we're all
Well,
stick
like,
pigs.
if it gives you 2, like,
If
it's 23
But
degrees.
when you convert it to Kelvin, it's still going to have probably 3 because you're using decimals.
Okay.
Number of decimals. Okay, so we started off big picture reaction. We fought through the details and we're like, okay, we're looking for N. And then you had to say ideal gas law, but for the oxygen. Once you solved for N, you had to remember that was still about oxygen. Here's your oxygen. Use your stoichiometry to get to the question, which was asked about the solid potassium chlorate. It's the only thing that's really new here. Who feels like, give me a 1 out of 10, how do you feel about that? 10 like, I'm awesome, 1's like, I still don't know what we did. No, be honest. I mean, how else am I supposed to know? I cannot read your mind. If you don't have your hands up, you're holding up the class. Okay, I'm seeing what I need. All right, I want you guys to start the second one. Here. Start this with your friends at your table and see where we get here. This is actually number 1 on your notes sheet that I gave you underneath the questions we have been approaching for like a couple days now. So FYI, you do have this in front of you if you have your note sheet. How many thumbs up you made it this far? Okay, that's the easy part. What else have you done so far? Syrian. Okay, so plus 273, what is that? Okay, and what else?
Then I converted the numbers of mercury to 1 atmosphere.
And that is
1.02
1.02 atmospheres. All right, who's gone farther than this? Right, tell me what's next.
You have to figure out the introvert to use question mark and put that next. And then
Hold on, pause. How do you know? Okay, tell me your thought process before you get there. Like-
you have to figure out what is a gas. Oh, yeah.
No, you're right. You're so right. So you have to figure out what the gas is, right?
Yeah,
So
it's-
this is not a gas. This is magnesium chloride, which is still an ionic compound, solid. It's kind of like table salt. Think of it like that. So what did you think of?
The decomposition formula.
Okay, so what's the decomposition of magnesium chlorate?
The magnesium chloride into Stioch
And
codes per atomic concentration.
and the balance,
3 on those.
and that's it. Why do you think I did this example earlier? I want to make sure that you were still very comfortable with predicting products of gases or chlorates. All right, so then you said, okay, I have an oxygen, that's my gas, and then what did you conclude from there you need to find?
The moles of oxygen.
Okay, so the first question asked of us is what's the percent yield? Well, yield means products, right? Yielding products. These are our two products. Yeah? Okay, what already do we know was collected? 4 that's actually what's decomposed. That's our reactant. So we're going to start our reaction with our reactant and then go from there. What has already been collected? 5.94 liters of the gas. Well, now the gas is who? Oxygen. Okay, so we can do this in two ways. Either, like Frank said, look for N of oxygen, which is kind of a secondary question, or we can actually start with liters and backtrack. But we'll start with whatever way is comfortable with you guys, because it's going to come from your heart here. So I'm hearing Frank say you want to do what? Okay, so you want to use this information to solve for N. Okay, so we're going to use the ideal gas law, keep this on our T, solve for N. N of oxygen is equal to, what's this rearranged? PV over RT. That's just us dividing by RT on both sides. Plug. Tell me when I'm plugging. Quickly. 0.018. Okay. You're good. 1.018 atmospheres. Okay. Okay. And when you plug in, and this is a little repetitive, we've done the ideal gas law a number of times today. When you're solving for this N, this is where you have to identify, is this the actual moles of gas I collected, or is this like theoretically what I should be able to produce if that much decomposed? Which is that? This is the actual moles I collected, because this is the actual liters I collected in the lab. I actually collected that. So this being actual yield of liters means that the correlating moles based on the calculation is still the actual amount of moles I collected, which I need a number for this.
0.0688.
Oh, say again.
68664.
Got you. Okay, so here's where our next thought process comes into play. I just took information, I saw it, I saw the ideal gas law, I slapped in the ideal gas law formula. I see this as moles of oxygen. That correlates with the liters of oxygen I collected. I'm still going to write this as actual yield, so you don't forget that's actually how much I collected in the lab. Now, where did that come from? Supposedly. Our what? Which was including the what reaction? Decomposition of magnesium chlorate, right? Well, Cassie, you want to help me out here?
I'm just confused on why couldn't you just do what we've been doing and do like 5 grams and then do like the conversion of moles and then do that.
We're going to do that. Yeah, hold on. So that's what I'm looking for. So this is the only value we haven't used yet, right? Correct? So we have to actually need to see, theoretically, if I have that much magnesium chloride, how much should I be able to produce? Does that make sense? how much oxygen should I produce, and what am I going to call that? That's the theoretical yield. If I were perfect in all ways, how much oxygen should I be able to produce? I'm going to compare it to what I actually produced, and then I'll do my percent yield from there. You got me? It's nice to think ahead and then actually do the math part, okay? So this right here I need to take and do, like, I think what you're telling me to do. Just stoichiometry. So here we go. This 4.5 grams of magnesium chlorate just needs to be converted to moles of oxygen so I can actually compare those, because I can't compare apples to oranges. I got to compare apples to apples. So how am I going to, or what's my next step here? Okay, go to moles, sorry. What's my molar mass? I don't know this one off the top of my head like I did the other, so I need somebody to help me here. What is it? 191.2. Is that close? I'll wait. You guys calculate because you guys are slacking. I got two or three people helping me calculate. I need at least a second or a third opinion before I keep going and embarrass myself because I didn't check your math. .21. Good luck. Just good job at knowing. Thanks, guys. You're welcome. Okay. Now, I got my grams to moles of magnesium chlorate. We still don't care about magnesium chlorate. It's not the gas. So, magnesium chlorate grams are gone. What's my next step if I want to get to my gas? The mole ratio. The mole ratio is between what and what? Okay. So, I'm seeing right here, I have a 1 in front of magnesium chlorate. I have a 3 in front of oxygen. How do I employ that down here? 3 moles of oxygen on top and magnesium chlorate on the bottom. Hallelujah. I have gotten to moles of oxygen. Why am I stopping at moles of oxygen? What tells me to do that? Because I have moles of oxygen here, and that's what I'm comparing, so they must be in the same units. So, calculadora. Point what? Okay, so, and this again is my what yield? This is my theoretical yield. Oh look, how convenient. I kind of have it aligned. My actual yield, 0.0686 blah blah blah. How do I get percent yield again before I tell you? That's percent yield. Just actual over theoretical times 100. And we have our actual and we have our theoretical times 100. You guys tell me your percent. Say it one more time. Sounds about right. Can I get a second on that? Okay, so I like to share all my work. 97-ish% yield. Would you want that person in your lab? Heck yeah. What's up?
So, if we had gone one step further and done 22 oxygen per mole.
Can't do that because I'm not at a CP.
Yeah.
Good. All right, so the question was, can I use the 22.4 liters and compare liters? Not in this case, because it's not an STP, but you could have done this another way, but I think this way it actually makes the most sense, so I'm going to stick with that. All right, so proceed. How much more time do I have in class? I'm making sure I'm not running over here. We have 5 minutes left in class. Here's what I'll ask you to do. Listen up and pull out your reference, not your reference, but your lecture notes, so I know that you know where we are here. It's the paper you've been working with for a little while. Okay, so you see 1 through 5 there on the very bottom right-hand side? Yeah. There was the ideal gas law started chemistry lecture practice. We just did 1. I thought we would get to like 4, but we tried. I want you guys to do 2, 3, and 4. I'll do 5 later with you guys. 2, 3, and 4. And just like normal, minimum expectation is that you are going through and you are writing those reactions and you're writing down your givens and you're trying to figure out the formulas that apply. Even if you can't get to the final answer, which you guys can see over on the bottom, I think you can still do 90% of it, and then if a gap here and gap there, I get it. And I'll be honest, like this right here, when I look for it tomorrow, I will give you a 0 if I don't have any, like if I don't have at least that much, because that's what I'm expecting from you, okay? And a lot of you guys, I was telling you just with your straight counter request, you know a lot of the process, and even if you're like, oh man, I can't remember the charge of fluoride or something, I give lots and lots of partial credit. Like I had people, you know, write it down 75% of the work with no numbers, just units, and I gave them most of their credit on their test, as much as I could. So there's a lot of things I can give you. It's just hard to give you anything for nothing. Okay? So go ahead right now. I would start processing a little bit number 2 or 3. You might even find one that's limiting reagent. Okay? So work through that for yourselves. We'll put our laptops up in the next couple minutes.